In this video, I will solve a Fredholm integral equation. The Fredholm integral equation is written as u of x is equal to f of x plus a to b k x t u of t dt. This is our Fredholm integral equation. In Fredholm integral equation, the lower limit is constant and the upper limit is also constant. We solve this by variational iteration method. The first assumption that we need to make over here is the kernel is degenerate kernel. The degenerate kernel is such kernel which is written as g of x and h of t. We put the value in equation number 1. U of x is equal to f of x plus a to b g of x h of t u of t dt. And from here we can write f of x plus g of x a to b h of t u of t dt. The reason of making this kernel degenerate, this term is called degenerate kernel. A kernel which is written as explicit for x and t. Since the limit is constant, the lower and upper limits are constant. So if we develop a theory, variational theory, we apply delta over here. So this will become a this will become a zero since we have lower and upper limit equal to constant. When we solve it at the end, we get some constant value. So one assumption is we need to survive this term, we need to make kernel equal to degenerate. All the other theory remains the same. First, we need to convert this equation 2 into the integral differential equation like this. U dash x, we take a derivative, f dash x plus g dash x a to b h of t u of t dt. So this is our equation number 3. So next we write correction functional equation for such integral differential equation, which is equation number 3. And from here we can write, for example, un plus 1 is equal to un plus 0 to x lambda xi un dash xi minus, then we have this term f dash xi minus, then we have this term since we changed the variable over here, so this becomes g dash xi a to b h of t u of t. I'm sorry, it should be some other variable. It is, for example, h of r, u of r, dr, and this whole dxi. And we have this u as a tilde over here, which is modified u, so on. So this is the theory, and theory remains the same for Lu is equal to, if it is first derivative, du by dx, then we have lambda is equal to -1. When we have second derivative, Then we have lambda is equal to xi minus x and so on. Generally, we work in second order differential equation, but if you needed third derivative, the lambda for third derivative, then you can get it very easily. The formula that we already discussed in previous video. So we solve first example. Example number 1. Example. We have a Fredholm integral differential equation. U dash is equal to e raised to power x minus x plus x 0 to 1 t u of t dt. This is equation number 1. I'm sorry, this is not first order integral differential equation. We have to make this integral differential equation. This is integral equation. In fact, this is integral equation. We differentiate both sides. We get u dash x is equal to e raised to power x minus 1 plus 1 0 to 1 t u of t dt, which is equation number 2. We find the correction functional equation un plus 1 un minus 0 to x un dash xi minus e xi plus 1 minus 0 to 1 r un r dr, and this is dxi. Okay. Since we have first order derivative over here, so lambda is equal to minus 1. That's what we have over here. So from this, when n is equal to 0, we get u1 u0 minus 0 to x du 0 by dxi minus e raised to power xi plus 1 minus 0 to 1, and this is r du 0 by dr, and we have dxi. When we solve that, we need also initial guess, and the initial guess is u naught is equal to 1. Where did we get this initial guess? You can get this initial guess by putting x is equal to 0 over here. So we get u of 0, e raised to power 0 is 1, this is 0, this is 0. So we get u of 0 is 1, which is initial condition of the integral equation, and this initial condition act as a initial approximation. So finally we get u1 is equal to e raised to power x minus x by 2. Similarly, when n is equal to 1, we get u2. I think you can get it yourself. It is not very difficult. We get e raised to power x minus x over, it will be 6 e raised to power x minus x over 2 cross 3. Similarly, when n is equal to 2, we have u3 e raised to, I'm sorry, okay, I just write the answer. So it will be ex minus 1 over 18 x, and this can be written as minus 1 over 2 cross 3 square x. Similarly, when we have n is equal to 3, we have u4, and the answer is ex minus 1 over 54 x, and this can be written as minus 1 over 2 cross 3 raised to power 3 x. And the n plus 1 un answer is maybe un plus 1 answer is e raised to power x minus the generalization of that 1 over 2 cross 3 raised to power n. N is greater than or equal to 0. So when I apply limit, there are two options. Either you can write un over here, You can make a formula by using un or either un plus 1, un plus 1, un plus 2, whatever you prefer to write the formula for. Limit n approaches to infinity, and we have un plus 1. Let me just check whether n plus 1 is correct or not. When n is equal to 0, we have u1 e raised to power x 1 over 2 cross 3 raised to power 0. So u1 should be ex minus x by 2. Okay. When n is equal to 1, we have u2 ex minus 1 over 2 cross 3. So we have 6. Correct. So it means this is correct. Okay. So un plus 1, and then we have, when we apply the limit n approaches to infinity, e raised to power x 1 over 2 cross 3 raised to power n. So from here we get ex. So this is the solution of our Fredholm integro-differential equation. Okay. Next we solve another example. We have over here example u of x is equal to sine of x minus x plus x 0 to pi by 2 u of t dt. This is equation number 1. We differentiate to get the integral differential equation. U dash x is equal to cos of x minus 1 plus 1 0 to pi by 2 u of t dt. This is equation number 2. Since this is first order differential equation, so lambda is equal to minus 1, and u of 0, when I put x is equal to 0 over here, you get u of 0 is 0. So it means that initial approximation is equal to 0. We write the correction functional equation. I do not want to repeat that over here. U naught x is equal to 0. Then for n is equal to 0, we get u1 sine x, maybe the formula first, u of 0x minus 0 to x du 0 by dxi minus cos xi plus 1 minus 0 to pi by 2 u0 r dr and dt. And when I put u naught is equal to 0, you get u1 is equal to sin x minus x. Similarly, n is equal to 1, we have u2 is equal to sin x minus x plus x minus pi square by 8x. Similarly, we have n is equal to 2, u3 is equal to u2 minus 0 to x, u2 dash xi minus cos xi plus 1 minus 0 to pi by 2 u2r dr dxi. So the answer is sin x minus x plus x minus pi square by 8x plus pi square by 8x minus pi square by 64x. So the reason was to write this as u3, or to put n is equal to 2 and 3, just to get the answer, just to get the pattern. We can see that minus x plus x will be cancelled out, this will be cancelled out, and so on, and it will continue cancelling out the next term. This is called actually a telescopic sum. So the solution is u of x is equal to sine of x. This is the exact solution of our integral differential equation. Okay, so this was all about the variational iteration method for Fredholm integral differential equation. Thank you for watching.